time it takes you to read this sentence, a star somewhere in the observable universe just died. Not quietly, not gradually. In a fraction of a second, a core the size of Earth crushed itself down to a ball 12 miles across, and the energy released in that single moment outshone every other star in its galaxy combined. Hundreds of billions of stars, swamped by one explosion. The shockwave tore through the outer layers of the star and hurled them into space at 10% the speed of light. And somewhere in that violence, in temperatures pushing into the billions of degrees, atoms were being built that could not be made any other way. Gold, platinum, uranium, the iodine in a human thyroid, all of it forged in seconds inside a dying star. This happens roughly twice a century in a galaxy like ours. Somewhere out there, right now, a star is in its final hours. It has been burning for millions of years. It has spent that entire time in a war, and the war is about to end. The war is between two forces. Gravity pulls inward. It always has. It wants to compress the star into the smallest, densest thing possible. The only reason it has not done that yet is that the star is burning, fusing lighter elements into heavier ones, releasing energy, pushing outward against the crush. For most of a star's life, those two forces balance. The gravity and the outward pressure hold each other at a standstill. The star sits there, stable, pouring light into space for millions or billions of years, and from the outside, it looks like nothing much is happening. But that truce is bought with fuel. Every second the star is burning through something, and the supply is not infinite. The fusion process climbs the periodic table in stages, running through one element, exhausting it, moving on to the next. Each stage buys time. Each stage is shorter than the last. The star is not stable. It is a controlled disaster, and the control is running out. When the fuel is finally gone, when the star has climbed as far up the periodic table as physics will allow, gravity wins. The core collapses in under a second, not slowly, not over years. In the time it takes your heart to beat once, a stellar core containing more mass than our entire sun shrinks from the size of a planet to the size of a city. The density at that point exceeds anything else in nature short of a black hole. A single teaspoon of that material would weigh more than 1 billion tons. The temperatures spike to numbers that have no human reference point. And then, the rebounding shockwave tears the rest of the star apart. What gets scattered into space is not just the star's outer layers. It is the entire chemical history of that star, millions of years of nuclear forging, plus everything the explosion itself built in those final frantic seconds. That debris drifts outward for thousands of years, mixing into the surrounding gas clouds, seeding the next generation of stars and planets with elements that didn't exist before. The universe does not start over clean after each cycle. It inherits the ashes. You are part of that inheritance. The calcium in your bones and the iron in your blood were forged in stellar cores and blasted into space by explosions that happened before our solar system existed. You are, in a very literal sense, made of the aftermath of stellar violence. That is what a supernova is. That is what it does. And the question worth sitting with is not what happens during one, but what causes it. What finally tips that ancient balance between pressure and gravity after millions of years of stalemate? To understand what breaks that truce, you have to start at the beginning, with what a star actually is. A star is not a thing that burns the way a candle burns. A candle consumes wax and oxygen and gives off heat and light and eventually goes out, and the world around it is unchanged. A star is doing something far more violent, far more precarious, and far more important than that. What you are looking at when you look at a star is a controlled disaster held together by competing forces that have been in a standoff for millions of years. The moment that standoff ends, everything changes. To understand what a star actually is, you have to start with gravity. Gravity is patient. It has one job, and it never stops doing that job, which is pulling everything toward everything else. In a cloud of gas drifting through space, gravity is quietly winning all the time. Hydrogen atoms drift slightly closer together. The cloud grows denser at its center. As it gets denser, gravity gets stronger, and the process accelerates. The gas at the center compresses. Compression heats things up. Keep compressing long enough, and that central temperature climbs into the millions of degrees. At a few million degrees, hydrogen nuclei are moving fast enough that when they collide, they don't just bounce off each other, they fuse. And that is when the second force enters the room. Nuclear fusion releases energy. Not the way burning releases energy, not the way a chemical reaction shuffles electrons around and throws off some heat. Fusion converts a small fraction of the mass of the nuclei themselves directly into energy. This is Einstein's equation working at full scale. When 4 hydrogen nuclei fuse into one helium nucleus, the helium nucleus weighs slightly less than the 4 hydrogens did. That missing mass becomes energy, and the amount of energy per unit of mass is staggering. A single kilogram of hydrogen fuel, if fully converted through fusion, releases roughly as much energy as burning 4 million tons of coal. Our sun is fusing around 600 million tons of hydrogen every single second. The energy that produces pushes outward in every direction. It is the only thing standing between the sun and complete gravitational collapse. This is the equilibrium. Gravity pulls inward. Fusion pressure pushes outward. The sun sits at a precise balance point between those two forces, and it has held that balance point for nearly 5 billion years. From the outside, this looks like stability. The sun rises every morning. It shines steadily. Nothing appears to be happening. But the apparent calm is an illusion, because what is actually happening in the core of our sun right now is an unbroken chain of nuclear explosions, releasing 4 million tons of mass as energy every second of every day. The stability you see is the surface of something catastrophic, kept perfectly in check. Now feel the scale of what you are dealing with. Our sun contains 99.8% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust drifting in the outer reaches, adds up to the remaining 0.2%. You could line up 109 Earths across the face of the sun. A commercial aircraft flying at cruising speed, non-stop, would take roughly 200 years just to circle it once. By any scale that registers to a human being, the sun is an incomprehensible object. And yet, the sun is a small star. There are stars hundreds of times more massive, thousands of times wider. The sun is what physicists call a yellow dwarf, which is the astronomical equivalent of being average in a category where average is already beyond comprehension. What holds all of that mass up is not a structure. It is not a shell, not a container, not a surface you could stand on. It is pressure, generated continuously, renewed every second by the fusion happening in the core. Stop the fusion, even briefly, and gravity does not pause to wait for it to restart. Gravity is always there. The outward pressure has to be there too, every second, or the collapse begins. This is what makes a star fundamentally different from anything you encounter in daily life. Every object you interact with sits in a stable state. A rock, left alone, remains a rock. A building, left alone, stands until something actively damages it. A star is not like this. A star is in a constant state of near collapse, held back only by the ongoing violence of its own fusion. It is less like a building and more like a spinning top. A spinning top stands upright only because it is spinning. The moment it stops, it falls. A star shines only because it is fusing. The moment it stops, it falls inward. The fuel is not unlimited. This is the point that everything else flows from. A massive star has an enormous amount of hydrogen, but enormous is not infinite. The fusion is consuming it continuously, relentlessly, and the star has no mechanism to stop the consumption, slow it down, or stretch the supply. What the star can do is burn other fuels when the hydrogen runs low, heavier elements that can also release energy through fusion, at least for a while. But each successive fuel buys less time. The reserves get smaller, the burning gets faster, and the endpoint draws closer. The star is not a stable object sitting calmly in space. It is a timed event, always moving toward the moment when the pressure fails and gravity wins. The fire keeps the house standing, and the moment the fire goes out, the house comes down. A star, more than 8 times the mass of our sun, does not burn one fuel and stop. It runs through a sequence of fuels, one after another, each one igniting only after the previous one has been exhausted. Think of it less like a single bonfire and more like a relay race, where each runner hands off to the next the moment their legs give out. The stages are predictable. The physics is settled. What isn't obvious until you look closely is the timeline. Each stage is dramatically shorter than the one before it. The star burns through its first fuel over millions of years. The last fuel lasts hours. That compression of timescales is not an accident. It is what a star in free fall toward its own destruction looks like from the outside. Hydrogen is where it all starts. In the core of a massive star, hydrogen nuclei fuse into helium, releasing energy, pushing outward, holding the star up. For a star 10 or 15 times the mass of our sun, this stage lasts roughly 10 million years. That sounds enormous. In cosmic terms, it isn't. Our sun has been fusing hydrogen for almost 5 billion years and has another 5 billion to go. A massive star runs hotter, burns harder, and exhausts its hydrogen supply in a fraction of that time. The core temperature during hydrogen burning sits around 10 million degrees. The core is dense, hot, and for now, stable. But the hydrogen can't last forever. When it runs out, the core has nothing left to push back with, and gravity squeezes it tighter. The temperature climbs. At around 100 million degrees, helium begins to fuse. 3 helium nuclei collide and merge to form carbon. It is a process called the triple alpha reaction, named because helium nuclei are also called alpha particles. Helium burning in a massive star lasts roughly 1 million years. Already we have dropped from 10 million years to 1 million. The star doesn't notice. From the outside, nothing dramatic has changed. The star keeps shining. But deep inside, the fuel mix has shifted and the clock has accelerated. a shell of unburned hydrogen still surrounds the helium-burning core, fusing at its own rate. The star is already beginning to develop layers. This is the onion structure. Each time the core exhausts one fuel and ignites the next, the previous fuel doesn't disappear. It persists in a shell surrounding the new burning region. Hydrogen in one shell, helium in another, carbon beginning to accumulate at the center. The shells are not static. They each burn at their own rate, feeding material inward, stacking products beneath them. The star is not a uniform object anymore. It is a set of nested chemical reactors, each running at a different temperature, each feeding the one below it. Carbon ignites at around 500 million degrees. Carbon burning lasts roughly 1,000 years. The pace is accelerating noticeably now. Carbon fuses into neon, magnesium, and sodium. Neon then burns at around 1 billion degrees. Neon burning lasts roughly a year. 1 year, where carbon burning took 1,000. Each transition requires higher temperatures because heavier nuclei have stronger electrical repulsion between them. It takes more force, more heat to push them close enough to fuse. The core keeps contracting between each stage, and that contraction is what drives the temperature up. This squeeze isn't catastrophic yet. It is controlled, just enough compression to ignite the next fuel. But the squeezes are getting harder, and the fuels are running out faster. The star that had millions of years to spare is now spending them like loose change. Oxygen ignites next, at temperatures above 1 billion degrees. Oxygen burning lasts around 6 months. 6 months to burn through products that took millions of years to accumulate. If you could somehow see inside a massive star at this point, you would be looking at concentric rings of nuclear fire, each burning a different element, each feeding material downward toward a core that is quietly filling with something the star cannot use. The star is still enormous on the outside, a red supergiant puffed out to hundreds of times the width of our sun. But inside, the action is concentrating. The burning regions are tightening around a growing center of mass. The countdown is no longer in millions of years. It is not even in thousands. By this stage, the star has become something almost incomprehensible in its complexity. The interior is a web of overlapping nuclear reactions, each shell burning a different element, each feeding material downward at rates that dwarf everything that came before. The core temperature has climbed beyond anything that could have ignited earlier fuels. The pressure from overlying layers bears down with staggering force. The entire structure is unstable in ways that would seem catastrophic, yet it persists, held together not by equilibrium, but by the inexorable squeeze of its own weight. The star is still shining. From the outside, it still looks like a star. But the countdown has entered its final chapter, and nothing can stop what comes next. Silicon is the second to last fuel. Silicon burning requires temperatures above 3 billion degrees. The core has to contract hard to reach that threshold. When it does, a cascade of nuclear reactions tears silicon nuclei apart and rebuilds them into heavier products: chromium, manganese, cobalt, nickel, elements clustering at the top of the fusion ladder. These settle inward, building up a growing mass of the heaviest thing the star is capable of making. The surrounding shells are still burning. The whole structure is still stacked, hydrogen fusing on the outside, silicon burning at the very center, every other stage somewhere in between. Every layer is a record of a different chapter of the star's history. Every layer is still actively burning, and the innermost one is doing what none of the others could stop. Silicon burning lasts days, sometimes hours, and at the end of it, the core fills up with the one element that ends everything. Releases energy because the product is more tightly bound than what went into it. Think about what that means. When protons and neutrons lock together into a nucleus, the resulting nucleus weighs slightly less than the individual particles that went into it. That missing mass becomes radiation. That radiation is the pressure holding the star up. Every fusion reaction, from the very first hydrogen burning in the core all the way to the silicon shell smoldering in the star's outer layers, is doing the same fundamental thing, converting a tiny fraction of mass into energy. And that energy is the price of another moment of existence. The star is not burning the way a fire burns. It is losing weight. And the weight it loses is the only thing keeping it alive. Physicists have a way of mapping this. They call it the binding energy curve. Plot every element on a graph with atomic mass on one axis and binding energy per nucleon on the other, and you get a curve that rises steeply from hydrogen, crests somewhere near the middle of the periodic table, and then flattens out. The peak of that curve, the element where nucleons are most tightly bound, is iron. Iron 56, specifically. This is not a coincidence. It is a hard mathematical fact built into nuclear physics itself. Iron is the most stable configuration of protons and neutrons that can exist. Nature cannot build anything more tightly locked together. That sounds like a triumph. For a star, it is a death sentence. What this means for a massive star is brutal. Every element below iron sits on the upward slope of that curve. Fusing two lighter nuclei into something heavier means climbing that slope, and climbing the slope releases energy. Hydrogen to helium, helium to carbon, carbon to neon. Each step moves you closer to the peak. Energy pours out at every stage. The star captures it, radiates it, and stays inflated against gravity. But once you reach iron, you have reached the top. There is nowhere higher to go. Fusing iron doesn't produce something more tightly bound. It produces something less tightly bound. And that means instead of releasing energy, the reaction consumes it. The math that kept the star alive for millions of years has simply run out. This is the trap. The star has no way of knowing it's approaching a wall. Silicon burning proceeds exactly the way every prior stage proceeded. The core contracts, heats up, reaches ignition temperature, and fusion begins. For a few days, silicon nuclei are smashed into heavier isotopes, climbing the last rungs of the ladder. Small amounts of energy still flow out. The star holds its shape, and then the silicon is gone, and what remains is iron. A dense, inert accumulation of the most stable element in the universe, sitting at the center of a star that has spent millions of years learning only one trick: fuse the next thing. Here is what stops working. The iron core cannot fuse productively, not because temperatures aren't high enough. By this point, the core is running at several billion degrees. The temperatures are extraordinary, but temperature doesn't matter when the physics say no. Pouring more energy into an iron nucleus will not get anything back out. It just gets hotter. The star is still generating some pressure from the shells burning above the iron core, from oxygen and silicon still fusing in surrounding layers. But the core itself has gone dark. It is growing. It is accumulating mass, iron piling onto iron with every passing minute. It is doing nothing to hold itself up except sitting there. Gravity has been patient. For 10 million years, or 5 million, depending on the star's mass, gravity has been pressing inward against a wall of outgoing radiation pressure. The wall held. The star kept its shape. What you have to understand is the scale of what gravity is working against. A star 15 or 20 times the mass of our Sun, every gram of it pulling toward the center since the moment the star ignited. Fusion was always the answer. Fusion kept producing a new answer every time the last fuel ran out. Hydrogen bought millions of years. Helium bought a few 100,000. Carbon bought centuries. Neon bought a year. Oxygen bought months. Silicon bought days. Each fuel was shorter than the last. Each debt paid off faster. Each loan smaller than the one before it. Iron is not a smaller loan. Iron is the moment the lender stops accepting payment entirely. What happens next is not gradual. Think of a column holding up a structure that has been pressing down on it for as long as either has existed. The column has been strong enough, just barely, to hold everything above it. Remove the column, and the structure doesn't sway or settle. It drops. That is what iron does to a stellar core. The moment the core is dominated by iron, the outward pressure from fusion disappears. The weight of everything above, hundreds of thousands of miles of burning shells, turbulent gas, and accumulated stellar material, begins pressing down on something that can no longer push back. The star has been fusing its way up the periodic table for millions of years, and iron is where the road ends. When the iron core reaches roughly 1.4 times the mass of our Sun, something extraordinary happens, and it happens fast. Fast is not the right word, actually. Fast implies something you could watch. What happens next is measured in milliseconds, and the violence packed into those milliseconds is almost impossible to describe without the numbers feeling fake. The core has been building up iron for days. It has been sitting there, growing denser, growing heavier, waiting for the moment when electron degeneracy pressure, the quantum mechanical force that has been holding it up, simply runs out of runway. When it does, gravity takes over completely. And gravity, at this scale, is merciless. The core begins to collapse. Not slowly, not gradually. The outer edge of the iron core is falling inward at roughly a quarter of the speed of light. You are looking at a region roughly the size of Earth, thousands of miles across, and it is shrinking. Every millisecond, the boundary pulls inward. The temperature is already extreme by any standard, but as the collapse accelerates and the material compresses, the temperature spikes further. Within the first fractions of a second, the core temperature climbs past 100 billion degrees. That number is not a typo, 100 billion degrees. For comparison, the center of our Sun sits at roughly 27 million degrees. The collapsing iron core is thousands of times hotter than that, and it is still compressing. At these temperatures and densities, the iron nuclei themselves begin to come apart. High-energy photons smash into iron atoms and break them back down into simpler pieces. Helium nuclei, free neutrons, free protons. This process is called photodisintegration, and it is catastrophic for the star because it absorbs energy. The core has been fighting gravity for millions of years by releasing energy through fusion. Now the extreme temperatures are actually consuming energy, ripping apart what took so long to build. The collapse accelerates further. Then something stranger happens to the matter itself. The density is now so extreme that electrons, which normally have plenty of space to move, are being forced into direct contact with protons. When an electron and a proton collide at these energies, they combine. The electron is absorbed, the proton converts into a neutron, and a neutrino is released. This process happens on a massive scale, all at once, throughout the entire collapsing core. The core is being neutronized. Protons are vanishing, replaced by neutrons, and with every conversion, another neutrino escapes, or tries to. Neutrinos barely interact with ordinary matter. Under normal circumstances, a neutrino could pass through a light year of solid lead without stopping. But the densities inside the collapsing core are no low, near normal. They are so extreme that even neutrinos get trapped, at least temporarily. The core becomes opaque to its own neutrinos, and an enormous reservoir of energy begins to build up. What you have now, in the space of under half a second, is a core that has gone from stellar densities to something approaching nuclear densities. Stellar density means material roughly as dense as the Sun, already far beyond anything on Earth. Nuclear density means matter packed as tightly as the nucleus of an atom. The gap between those two states is enormous, and the core is crossing it in real time. A teaspoon of core material at this stage would weigh somewhere in the range of 1 billion tons. The entire iron core, originally the size of Earth, is now collapsing toward the size of a city. The rest of the star does not know this yet. Remember that the star is massive. The outer layers of silicon, oxygen, neon, carbon, helium, and hydrogen are still sitting where they were. The collapse at the center is happening so fast that the information hasn't reached the surface. Light takes 8 minutes to cross our solar system. The star's outer layers are enormous. The signal from the collapsing core, traveling outward at the speed of sound through the stellar material, has not arrived yet. The outer star is, for a brief moment, completely unaware that the floor beneath it has dropped out. It is still structured the way it always was. It is still an onion. It just no longer has a center worth mentioning. This is worth holding in your mind because it tells you something about the scale of what is happening. The most violent event in the life of the star is completely invisible from the outside for the first fraction of a second. The photons that will eventually signal the explosion have not started moving yet. If you were watching this star from a telescope right now, you would see nothing unusual. The surface would look the same as it did yesterday. Meanwhile, in the core, the collapse is still going. The density is still climbing. The temperature is still climbing. Neutrinos are flooding outward in numbers that are genuinely difficult to put into words. We are talking about 10 to the power of 58 individual particles, carrying off an enormous fraction of the total gravitational energy being released. The core is radiating more energy in neutrinos in these first few seconds than our Sun will release in its entire 10 billion year lifetime. Almost none of it, under normal circumstances, would interact with anything on its way out. But the circumstances here are not normal, and what happens to that neutrino flood in the next few seconds will determine whether the star explodes at all. In under a second, a region the size of Earth has compressed into a ball roughly 12 miles across, and the collapse is not finished. The collapse cannot go on forever because matter has limits. As the iron core shrinks below roughly 12 miles across, something extraordinary pushes back. The individual neutrons packed into that space begin to feel each other in a way that has no equivalent at normal densities. Nuclear matter obeys rules that ordinary matter does not. When nucleons, protons and neutrons, are forced to within about a femtometer of each other, the strong nuclear force switches from attractive to repulsive. the core is no longer compressible. In the space of milliseconds, a region that was collapsing at a significant fraction of the speed of light hits something that might as well be a wall of solid iron, 1,000,000,000,000 times denser than iron has any right to be. Physicists call this nuclear degeneracy pressure, and it is the most abrupt stopping force in the known universe. The core does not just stop, it overshoots and bounces. Think of it like a rubber ball compressed beyond its natural limit and then released. Except the ball here is a ball of pure neutrons roughly 12 miles across, and the energy it releases in that rebound is staggering. In under a millisecond, the innermost core snaps back outward. The material falling inward from the outer layers of the star is still racing toward the center at tens of thousands of miles per second. It collides with the rebounding core. That collision produces a shock wave. This is the bounce, and in theory, this shock wave is the explosion. The shock forms at the boundary between the rigid inner core and the still infalling outer layers, and it begins driving outward at roughly 1/10 the speed of light. For a fraction of a second, it looks like the problem is solved. Something is moving outward with extraordinary violence, plowing through the material above it, pushing toward the surface of the star. If you could watch this at the right scale, the shockwave would look like a nearly circular pressure front, expanding outward from the center, compressing everything in its path, heating it to temperatures above 100 billion degrees. The outer shells of silicon, oxygen, neon, carbon, helium, and hydrogen are all sitting above this expanding front. The shockwave is heading toward all of them, but then it starts to slow. The outer core is not empty. It is packed with iron nuclei that have not yet collapsed, still falling inward, still dense, still in the way. The shockwave has to smash through this material, and smashing through it costs energy. Every iron nucleus the shockwave hits gets ripped apart, photodisintegrated in the technical language, broken back down into individual protons and neutrons. This process consumes energy at a brutal rate. It takes roughly 1.7 times 10 to the 24th ergs to disintegrate each gram of iron. The star's outer core contains roughly half a solar mass of iron nuclei, all of them waiting to absorb energy from the shockwave as it passes through. The numbers are crushing. Estimates suggest the shockwave loses somewhere in the range of 10 to the 51 ergs just to photodisintegration, which is roughly as much energy as our sun will radiate over its entire 10 billion year lifetime. There is a second problem. The density near the core is so extreme that even the neutrinos being produced in enormous quantities by the collapse cannot escape instantly. They pile up just outside the core in a region called the neutrino sphere, and as the shockwave moves outward past this region, it begins driving material into a zone where those trapped neutrinos stream outward and carry energy with them. The shockwave, which was already bleeding energy to photodisintegration, is now also losing energy to the neutrino wind. Within roughly 10 milliseconds of the bounce, the shockwave has stalled. This is the puzzle that has occupied computational astrophysicists for decades. The collapse produces a bounce. The bounce produces a shockwave. The shockwave should drive the explosion. But the shockwave stalls. And a stalled shockwave means no explosion. It means the outer layers of the star simply slow, fall back inward, and pile onto the proto-neutron star sitting at the center. In a simulation that does not account for anything beyond the pure hydrodynamics of the bounce, the star does not explode. It collapses further. The core grows heavier. The star dies quietly, swallowed into itself. No supernova, no light, nothing. And yet supernova happen. We have seen them. The galaxy is littered with their remnants. Whatever process revives the stalled shockwave is real, because the evidence that the shockwave eventually escapes is written across the sky in the Crab Nebula, in Cassiopeia A, in every expanding shell of gas still glowing from an explosion thousands of years ago. Something saves the explosion. What that something is remains one of the most actively debated problems in high-energy astrophysics. The simulations get more sophisticated every year, and the answer keeps looking like it involves multiple things working together simultaneously. Convection, turbulence, hydrodynamic instabilities, and the enormous flood of neutrinos streaming out from the proto-neutron star. The neutrinos are carrying away 99% of the gravitational energy of the entire collapse. Even if a tiny fraction of that energy gets deposited back into the stalled shockwave, the numbers might be enough. But that is the next question. For now, the shockwave sits frozen inside the outer core, suspended somewhere between the rebounding neutron star below it and the dense stellar material above it. The outer layers of the star have no idea what is happening beneath them. The star still looks intact from the outside. The explosion is technically underway and technically failing at the same time. The shock stalls somewhere in the star's outer core, and for a fraction of a second, the explosion hangs in the balance. The energy released in a core collapse supernova is almost impossible to hold in your head. In the fraction of a second that it takes the core to collapse, the star releases more energy than our sun will radiate across its entire 10 billion year lifetime. Not 10 times more, not 100 times more, roughly 10,000 times more energy, compressed into a single violent moment. Most of that energy does not come out as visible light. It does not come out as heat or radio waves, or any radiation you can easily picture. It comes out as neutrinos, and if you have heard of neutrinos before, you probably heard that they pass through everything. That part is true, but it is only half the story. Neutrinos are subatomic particles with almost no mass and no electric charge. Billions of them are passing through your body right now, produced by fusion in the sun, and not one of them is stopping. They move at nearly the speed of light, and they interact with ordinary matter so rarely that a light year of solid lead would stop only about half of them. This is the problem. When the collapsing core produces its flood of neutrinos, they should simply pour out of the star and vanish into space, carrying all that energy with them and leaving the stalled shockwave with nothing to work with. And yet the star explodes. Something is bridging the gap. Here is where the numbers start doing something unexpected. When the core collapses and the neutron star forms, it releases roughly 10 to the power of 58 neutrinos. Write that out, and the number becomes essentially meaningless to a human brain. What matters is the energy those neutrinos carry, which is somewhere around 3 times 10 to the 46 joules. The shockwave sitting just outside the core, stalled and losing ground against the infalling material above it, needs only about 1% of that energy to revive and push through. The question is whether even 1% can be deposited before the neutrinos escape. Normally, the answer would be no. Neutrinos are ghost particles. They do not care about your detector or your star. But the region just outside the newly formed neutron star is not like anything else in the universe. The density there is so extreme, the material so tightly packed, that even the near weightless, near invisible neutrino finds it difficult to pass straight through. For a brief window of time, measured in milliseconds, the neutrino opacity of that region is high enough that neutrinos begin to transfer energy to the surrounding gas. A tiny fraction of them scatter, a tiny fraction deposit their momentum. But the flood is so overwhelming, so relentlessly enormous, that even that tiny interaction rate turns into something real. The stalled shock begins to absorb energy. The gas behind it heats up, pressure builds, the shockwave starts moving again. This mechanism has a name. Astrophysicists call it neutrino-driven convection, and alongside it, a process called the standing accretion shock instability, which creates turbulence behind the stalled shock that helps funnel neutrino energy into the explosion. The theoretical details are still being worked out in supercomputer simulations that take months to run. But the basic picture has been confirmed, and it was confirmed on a single night in February of 1987. Sen, 1987. A was a supernova in the Large Magellanic Cloud, a satellite galaxy of the Milky Way sitting roughly 168,000 light-years away. When it exploded, neutrino detectors buried in mines in Japan, Ohio, and Russia each recorded a sudden burst of detections. Kamiokande 2 in Japan caught 12 of them. The IMB detector in Ohio caught 8. A smaller Soviet detector caught 5. 24 neutrinos in total across 3 separate instruments, all arriving within a window of about 12 seconds. 24. From 10 to the 58. That is what the detectors saw out of the entire flood, and it was enough to confirm everything. The arrival of the neutrinos came 3 hours before the light from the explosion reached Earth, which matched the theory exactly. Neutrinos escape the core directly. Light has to wait for the shockwave to reach the star's surface. 24 particles changed our understanding of how stars die. Without that neutrino energy transfer, current models suggest the shockwave simply does not make it. It stalls, the infalling material overwhelms it, and the star collapses entirely into a black hole without producing much visible explosion at all. The neutrino mechanism is not incidental to the supernova. It is the supernova. Neutrinos barely interact with anything in the universe, and yet without them, the explosion probably never escapes. After the explosion, 2 things remain: a rapidly expanding shell of gas and whatever the core left behind. The outer layers, the hydrogen, the helium, the carbon and oxygen and silicon that spent millions of years burning in nested shells around the core, all of that gets hurled outward at somewhere between 9,000 and 25,000 miles per second. It will keep expanding for thousands of years, sweeping up surrounding gas, glowing, distributing the newly forged elements into the interstellar medium. But the core does not go anywhere. The core stays. And what the core becomes depends on one thing: how much mass is left when the collapse is finished. If the remaining core mass settles below roughly 2 to 3 times the mass of our Sun, something extraordinary holds. The neutrons themselves push back. Neutron degeneracy pressure, a quantum mechanical effect, the same kind of pressure that holds white dwarfs up, but operating at a far more extreme scale, stops the collapse cold. What you are left with is a neutron star, and neutron stars are among the strangest objects the universe knows how to make. The numbers are almost meaningless the first time you hear them. A neutron star typically packs somewhere between 1 and 2 solar masses into a sphere roughly 12 miles across. Our Sun, which contains 99% of all the mass in this solar system, has a diameter of 865,000 miles. A neutron star compresses that order of mass into something you could drive across in 15 minutes. The density is nuclear. Every cubic centimeter of the thing contains roughly 400 million tons of matter. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. There is no surface in any sense you would recognize. No rock, no liquid. Just a sea of neutrons packed as tightly as the interior of an atomic nucleus, stretching from edge to edge of the entire object. Now add rotation. The star that collapsed was already spinning. When the core shrank from something the size of Earth down to a city, it conserved its angular momentum. The same reason a figure skater speeds up when pulling in their arms. The result is a neutron star spinning at extraordinary rates. Some rotate several times per second at birth. The fastest known pulsars, neutron stars that beam radiation like a lighthouse, sweeping past Earth with each rotation, spin hundreds of times per second. The fastest on record completes over 700 rotations every second. That is not a typo. An object containing more mass than our Sun, rotating 700 times per second. If you could hear it, it would produce a tone well above middle C. Then there are the magnetic fields. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. That alone would be enough to stop most conversations. But some neutron stars go further. Magnetars, a specific class of neutron star, carry fields estimated at 10 to the 15th Gauss. For comparison, a strong hospital MRI machine runs at roughly 30,000 Gauss. A magnetar would begin to affect the electron structure of your atoms from half the distance to the Moon. They are the most intensely magnetized objects ever detected, and they occasionally release bursts of energy that, from thousands of light years away, are still powerful enough to measurably disturb Earth's ionosphere. One did exactly that in 2004, from 50,000 light years away, on the other side of the galaxy. Were we witnessing the actual moment of a star's death as it unfolded? Not exactly, but something real was left behind every time. That is the point. The neutron star is not a remnant in the way an ash pile is a remnant. It is a new object entirely, with physics that does not apply anywhere else in the universe at those scales. But not every collapsing core becomes a neutron star. If the mass left in the core after the explosion exceeds roughly 2 to 3 solar masses, the precise boundary is still debated. Then not even neutron degeneracy pressure is enough. Neutrons have limits just as electrons do. When the core mass crosses the threshold, the collapse does not stop at the neutron star stage. It keeps going. The neutrons get crushed. The density climbs past nuclear density, and there is no known force in physics capable of halting what comes next. The core collapses into a black hole. A black hole left behind by a stellar collapse is not a giant object. It starts as a remnant only a few times the mass of the Sun, compressed into a region smaller than a city, then smaller than that, all the way to a singularity, a point where our current equations break down completely and stop giving meaningful answers. The gravity near the event horizon is strong enough that light itself cannot escape. The neutron star that might have formed briefly simply vanishes behind the horizon as the collapse completes. There is no explosion at this stage. no flash. The core just disappears from the observable universe, and the only evidence it exists is the gravitational pull it exerts on whatever is nearby. What determines which of these two outcomes you get is the mass of the collapsing core. But that depends on how much of the outer star was ejected in the explosion, which depends on how much energy the neutrinos deposited into the shockwave, which depends on the rotation of the core and the composition of the progenitor star and the behavior of matter at nuclear densities that we can only partially model. Some simulations suggest that stars in certain mass ranges can produce black holes directly, skipping the dramatic visible supernova almost entirely. A star simply winks out. No explosion. Nothing left to see except the absence of something that used to be there. The boundary between which outcome you get is not a bright line. It depends on the progenitor mass, the spin, the composition, and factors that stellar physicists are still arguing about. Not every supernova begins with the death of a massive star. Everything covered so far, the iron core, the collapsing core, the neutrino flood, the neutron star left behind, that is one path. It is the path most people picture when they hear the word supernova. But the universe has a second path, and it starts with a kind of star that, by all appearances, is already dead. A white dwarf is what remains after a star like our Sun reaches the end of its life. Not every star goes out violently. Stars below roughly 8 times the mass of our Sun never build up an iron core. They never reach the conditions needed for collapse. Instead, they swell into red giants in their final stages, shed their outer layers into space, and leave behind a dense, compact core. That core is the white dwarf. No fusion is happening inside it. No fuel is burning. It is simply a remnant, a cooling ember the size of Earth, but carrying roughly the mass of the Sun, slowly radiating the last of its heat into the void. To understand why that matters, you have to understand what is actually holding the white dwarf up. Normal stars are held up by the outward pressure of fusion, the constant explosion in the core pushing back against gravity. A white dwarf has no fusion. What holds it up instead is something called electron degeneracy pressure, a quantum mechanical effect where electrons resist being compressed into the same space. It has nothing to do with heat or burning. It is a property of matter itself at extreme density. A white dwarf could cool to absolute zero and still not collapse, because the electrons would still refuse to be squeezed any tighter. That resistance is what makes the white dwarf stable. Stable, that is, up to a point. Here is the setup. In many stellar systems, stars do not form alone. They form in pairs, 2 stars orbiting a shared center of mass, close enough that their gravitational fields interact. These binary systems are common. Something close to half of all stars in the galaxy have a companion. When both stars in a pair are roughly the size of our Sun, they each go through their normal life cycles independently. Eventually, one of them burns through its fuel faster, swells into a red giant, sheds its outer layers, and becomes a white dwarf. The other star is still burning, and this is where things get interesting. A white dwarf sitting next to a living companion star is not really sitting still. Gravity between the two objects is pulling them toward each other constantly. If they are close enough, the white dwarf's gravity can begin pulling material off the surface of its companion. Gas from the companion's outer layers streams across the gap between the two stars and falls onto the white dwarf. Astronomers call this accretion. the white dwarf is feeding. The companion does not have to be any particular type of star. It can be a red giant, bloated and loosely bound, shedding its outer atmosphere easily. It can be a main sequence star, still fusing hydrogen, slowly losing material from its surface. In some cases, both stars in the pair end up as white dwarfs, and they spiral toward each other over billions of years until one begins transferring mass to the other. The specific setup varies. What does not vary is the consequence. Every time material falls onto the white dwarf gets heavier. This sounds slow. It is slow. The accretion rate in most of these systems is tiny, a fraction of the mass of our Sun transferred over millions of years. But a white dwarf has no way to relieve the pressure of that accumulating weight. A normal star, if you added mass to it, would simply expand slightly, heat up, and fuse a bit faster, absorbing the change. A white dwarf cannot do that. Its supporting pressure is not tied to temperature. Adding mass just means more mass pressing down, and the electrons resisting that mass have a limit to how hard they can push back. The material landing on the white dwarf does not just sit there quietly either. When hydrogen-rich gas falls onto the surface and the temperature and pressure climb high enough, small fusion reactions can ignite on the white dwarf's surface. You can get a nova, a sudden flare of fusion that blows off the accumulated layer in a burst of light, leaving the white dwarf slightly lighter than before. A nova is not a supernova. The white dwarf survives a nova. Some white dwarfs nova repeatedly over thousands of years, settling into a rhythm of accumulation and surface explosion. But in certain systems, the white dwarf gains mass faster than it loses it through these surface events. Net weight goes up, slowly, consistently, over timescales that dwarf recorded human history. And the companion star has no awareness of any of this. It is simply being orbited by a dead stellar remnant, losing a thin stream of its outer material to its partner's gravity, continuing to fuse its own hydrogen at a perfectly normal rate. Nothing about the companion's behavior changes as the white dwarf approaches the limit that will determine both of their fates. The companion is not reacting to what the white dwarf is doing. It cannot sense what is coming. The white dwarf is patient, sitting in its orbit, quietly gaining weight from its partner, and the partner has no idea what it is feeding. There is a number that governs the fate of every white dwarf in the universe, 1.4 times the mass of our Sun. That number has a name. Astronomers call it the Chandrasekhar limit, after Subramanian Chandrasekhar, a young Indian physicist who calculated it in 1930 while on a ship crossing the Atlantic. He was 19 years old. The number he arrived at describes something fundamental about the physics of matter under extreme compression, specifically the point at which the quantum mechanical force holding a white dwarf up against gravity simply cannot hold anymore. At one point, 4 solar masses, electron degeneracy pressure fails, and when it fails, everything that has been quietly accumulating on that white dwarf becomes relevant in the most violent way imaginable. To understand why that limit exists, you need to understand what is actually holding a white dwarf up. Normal stars are supported by the outward pressure of fusion, the constant energy release from nuclear reactions pushing against gravity. White dwarfs are different. The fusion stopped long ago. What remains is a dense ball of carbon and oxygen, roughly the size of Earth, held up not by burning fuel, but by a quantum mechanical effect. Electrons in the core resist being compressed into the same space. The more tightly you squeeze them, the harder they push back. This is called electron degeneracy pressure, and it has nothing to do with heat or burning. It is a property of matter itself. For a while, it works. A white dwarf sitting quietly in space can remain stable more or less indefinitely, slowly cooling over billions of years. But a white dwarf in a binary system, one that is stealing mass from its companion, is not sitting quietly. It is gaining weight. Slowly, steadily, the accreted material piles onto the surface. Carbon and oxygen accumulate. The white dwarf gets heavier, and the closer it gets to 1.4 solar masses, the more extreme conditions in its core become. Here is where the physics turns dangerous. As the white dwarf approaches the limit, the core temperature begins to climb. Carbon and oxygen, the two dominant components of the white dwarf's interior, have a fusion threshold, a temperature at which they begin to react with each other. In a normal star, this would not be a catastrophe. Normal stellar material expands when it heats up. Expansion cools things down. The reaction regulates itself. There is a built-in thermostat. A white dwarf does not have that thermostat. Electron-degenerate matter behaves differently. When you heat it, it does not expand. The pressure it exerts is not tied to temperature the way ordinary gas pressure is. So when the core gets hot enough to ignite carbon fusion, the fusion releases energy, the temperature rises, the fusion rate accelerates, and the temperature rises further. There is no expansion, no cooling, no feedback mechanism to slow anything down. The reaction cannot stop itself. It just runs. What happens next takes roughly 1 second. The fusion front tears through the white dwarf at a significant fraction of the speed of sound, consuming the star from the inside out. Within moments, it transitions from a smoldering ignition to a full detonation, propagating faster than the material can respond. Temperatures spike to billions of degrees. The carbon and oxygen that have been locked inside this dead star for possibly billions of years are suddenly all reacting at once. The energy released in those few seconds rivals what our sun will produce across its entire 10 billion year lifetime. The white dwarf does not collapse. It does not form a neutron star. It does not leave a core remnant of any kind. It tears itself apart entirely. The explosion is total. Every atom of carbon, every atom of oxygen, every heavier element synthesized in those frantic final seconds is thrown outward into space at velocities measured in tens of thousands of kilometers per second. The binary companion, if it survives the blast, is left orbiting nothing. This is also what makes Type 1a supernovae so valuable to cosmologists. Because the mechanism is standardized, every white dwarf that explodes this way does so at almost exactly the same mass. The explosions all reach roughly the same peak brightness. You can use them as measuring sticks. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is with precision that would be impossible otherwise. Astronomers call this a standard candle. Type 1. A supernovae are the most powerful standard candles we have, visible across billions of light years. The Chandrasekhar limit, a number derived from quantum mechanics, turns out to be the physical anchor that makes these measurements possible. Every white dwarf blows up at the same weight for the same reason in the same way. Nature, for once, is consistent. The entire white dwarf detonates in seconds, and unlike a core collapse supernova, there is nothing left behind. not a neutron star, not a black hole, nothing at all. When astronomers look at the spectra of supernova, they find something unexpected. Not all core collapse events look the same. The Type II supernovae covered so far leave a clear fingerprint. Hydrogen lines, bright and obvious, stamped into every spectrum. But a significant fraction of core collapse supernovae show no hydrogen at all. Some show no helium either. The star exploded. The mechanism was the same. The iron core collapsed. The bounce happened. The shockwave tore outward. But the outer layers that should have been there simply were not. Something had taken them. This is where stellar classification gets more specific. Astronomers divide these stripped supernovae into two categories based on what the dying star had left when it finally went. A Type 1b supernova is a star that lost its hydrogen envelope before the explosion, but still had its helium layer intact. The spectrum shows helium lines, no hydrogen. A Type YC is stripped further still. Hydrogen gone, helium gone, essentially down to the bare carbon and oxygen core by the time it detonates. The spectra of Type IC events are notably featureless compared to other supernovae, which sounds like a small technical distinction until you ask what that absence actually means. A star that was once many times the mass of our Sun arrived at the final moment of its life, with its outermost layers complete, lie missing. That takes either an enormous amount of time or an enormous amount of help. The first way a star loses its envelope is through its own wind. The most massive stars in the universe, those running at 60, 80, 100 solar masses or more, generate such intense radiation that they push their outer layers off continuously throughout their lives. This is not a slow, gentle process. These stars shed material at rates that would strip an entire solar mass of gas in a few 100,000 years. By the time such a star reaches the end of its fusion sequence and its iron core begins to accumulate, the hydrogen shell that once surrounded it has long since been blown into the surrounding nebula. What remains is a hot, dense, exposed core still burning through its final fuels. These stripped stars have their own classification. Astronomers call them Wolf-Rayet stars, and they are among the most luminous and short-lived objects known. When a Wolf-Rayet star collapses, the explosion that follows looks like a Type 1b or 1c, depending on how far the stripping went. But stellar winds alone cannot account for all of these events. The numbers do not work out. There are more stripped envelope supernovae than there are stars massive enough to lose their layers through winds alone. This is where binary companions enter the picture, and the picture changes considerably. A large fraction of massive stars do not travel through life alone. They orbit a companion, sometimes something comparable in mass, sometimes smaller, and the two stars spend millions of years in a gravitational partnership. If the orbital separation is close enough, the larger star swells as it ages, and its outer layers begin to overflow toward its companion. The companion accretes this material, gains mass, and the original star is gradually peeled back. This process is called mass transfer, and it is efficient. Over the course of millions of years, the companion can strip away the hydrogen envelope almost completely, leaving behind a helium-rich remnant still burning through the later stages of stellar fusion. When that remnant finally collapses, the explosion looks like a Type 1b. If the helium layer was also transferred or blown away, it looks like a Type 1c. What this means in practice is that the diversity of supernova types is partly a census of stellar relationships. A Type 2 supernova tells you the star died alone, or at least far enough from any companion that its outer layers were still in place at the end. A Type 1b or 1c tells you the star had a partner, or was so massive that it shed its own skin before the collapse. The spectra are not just chemical fingerprints, they are evidence of a whole history of interaction stretching back millions of years. There is something worth pausing on here. When astronomers watch one of these stripped supernovae brighten and fade, they are seeing the explosion of a core that was essentially naked when it went. No thick hydrogen atmosphere to plow through, no extended envelope to slow the shockwave. The ejecta expand quickly. The light curve rises fast. And somewhere in the vicinity, quite possibly still orbiting in the expanding debris, is the companion star that spent the better part of 1 million years pulling material off the star that just exploded. The stripped star dies the same death as any other massive star, but the partner that stole its outer layers may survive the explosion entirely, flying off into the galaxy at high speed. The standard picture of a supernova, already one of the most energetic events in nature, has outliers that make it look tame. Most supernovae peak at around the brightness of a few billion suns. That is already incomprehensible. But astronomers began finding explosions that peaked at 10, 50, sometimes 100 times that luminosity. Stars that briefly shone with the light of tens of billions of suns. Stars that didn't fade the way they were supposed to, holding their peak brightness for weeks or months instead of days. These events didn't fit any existing model. They were called superluminous supernovae, and the first confirmed examples were detected in the mid-2000s when automated sky surveys started catching objects that simply had no business being that bright. Nobody had a clean explanation. The physics that worked for ordinary core collapse events couldn't account for the energy output. Something else was powering these explosions from the inside. The leading candidate is one of the most extreme objects the universe produces. When a massive star collapses, the core that remains can become a neutron star. In most cases, that neutron star is dense and hot and gradually cools. But in some collapses, conditions produce something different. A neutron star with a magnetic field so intense, it defies easy comparison. Earth's magnetic field is roughly half a Gauss at the surface. The magnetic field of one of these objects can reach 10 to the 15th Gauss. That is a quadrillion times stronger. Astronomers call them magnetars. A magnetar the size of a small city contains the mass of the Sun compressed to nuclear density, spinning sometimes hundreds of times per second, wrapped in a magnetic field strong enough to distort the electron clouds of atoms from thousands of miles away. They are not a theoretical curiosity. We have detected them inside our own galaxy. What they do to a supernova is something else entirely. A newly born magnetar is a rotating reservoir of energy. The spin rate right after formation can be extraordinary. Some models suggest initial rotation periods of just a few milliseconds. As that rotation slows over days and weeks, the energy has to go somewhere. The magnetic field acts like a brake against the surrounding plasma, converting rotational energy into radiation and injecting it directly into the expanding shell of ejected material around the star. Think of it as a second engine inside the explosion. The initial blast blows the star apart. Then the magnetar, sitting at the center of the wreckage, keeps pumping energy outward for weeks, re-energizing the ejector and dramatically amplifying the total light output. The longer the magnetar spins at high speed, the more energy it do. MPS in the right conditions, a magnetar can contribute as much energy to the visible explosion as the initial collapse itself. That is why some superluminous supernovae stay bright far longer than any standard model predicts. The numbers attached to this process are worth sitting with. A typical core collapse supernova releases roughly 10 to the 44 joules of energy in visible light. A magnetar-powered superluminous supernova can exceed 10 to the 45 joules. The total rotational energy available in a rapidly spinning neutron star at formation is somewhere around 10 to the 46 joules, meaning the magnetar has more than enough reserve to account for the excess luminosity. The argument for magnetars isn't just theoretical. When researchers model the light curves of superluminous supernovae, plotting brightness against time and looking for the shape that matches, the magnetar model fits in a way that straightforward radioactive decay or shock heating simply doesn't. You can see the signature of a central engine in the data. Then there is the other category. Not every superluminous event requires a magnetar. Some of the most extreme explosions may come from stars so massive they push into a regime of physics that ordinary stellar evolution never reaches. Stars with masses above roughly 130 to 150 times the mass of the Sun develop cores so hot that the gamma-ray photons produced in the core begin doing something unexpected. They convert spontaneously into electron-positron pairs. Each photon that converts removes radiation pressure from the core, and the core, suddenly deprived of support, begins to contract. Contraction raises the temperature, which produces more pair creation, which removes more pressure. What follows isn't a slow collapse. It's a runaway thermonuclear explosion of unimaginable scale, a pair instability supernova that completely destroys the star. No neutron star, no black hole, nothing. The entire object, potentially containing more than 100 times the mass of our Sun, is converted into energy and thrown into space. Pair instability supernovae may have been more common in the early universe, when the first generation of stars was forming from nearly pure hydrogen and helium, and some of them grew to extraordinary masses before dying. Today's universe, enriched with heavier elements that influence how stars shed mass as they age, produces fewer stars large enough to reach this threshold. But the candidates exist. Stars above this mass range have been catalogued, and some of the most luminous transients ever detected carry the fingerprints of pair instability events, light curves that rise too slowly and fade too gradually to match any other mechanism, with total energy outputs that strain the upper limits of what a magnetar can supply. These events are still poorly understood, but they suggest that the range of ways a star can die is wider than the textbook version implies. The brightness of a supernova at peak is a number that does not mean much in isolation. 10 billion times the luminosity of the Sun. Say that out loud, and it still does not land. Numbers that large have nowhere to go in the human mind. So here is a better frame. At peak brightness, a single supernova can outshine every other star in its entire host galaxy combined. Not just most of the stars, all of them. Hundreds of billions of suns, burning simultaneously, and one explosion buries the whole collection. For days or weeks, that single point of light radiates more energy than everything else in a galaxy that took billions of years to build. To understand what that actually looks like, you have to go back to the historical record. In the year 1054, Chinese imperial astronomers wrote about a new star that appeared in the sky without warning in the constellation we now call Taurus. They called it a guest star. It was bright enough to read by. It was visible in full daylight for 23 consecutive days. At night, it cast shadows. This went on for nearly 2 years before it finally faded below naked eye visibility. What those astronomers were watching was a core collapse supernova roughly 6,500 light-years away. What remains of that explosion today is the Crab Nebula, a tangled cloud of glowing filaments still expanding outward nearly 1,000 years later. The 1054 event was not even the brightest supernova in recorded history. That distinction belongs to a supernova that appeared in the year 1006 in the southern constellation Lupus. Astronomers from Egypt, Iraq, China, Switzerland, and Japan all recorded it independently. Best estimates put its apparent brightness at somewhere between magnitude -7 and -9. For context, Venus at its brightest reaches about -5. This star was far brighter than Venus and bright enough to cast readable shadows on clear nights. It stayed visible to the naked eye for years. Now put one of those events in a modern context. Imagine a star in the Milky Way, a few thousand light-years away, goes supernova tonight. If you were standing outside and looked up, you would see a new star appear, probably in or near the plane of the galaxy, and within hours, it would be brighter than anything else in the sky. By the time it peaked, it would outshine the full moon. On a clear night, it would throw your shadow against the ground. During the day, you could cover the sun with your hand and still see it. Every telescope on Earth and in orbit would pivot toward it immediately. Every neutrino detector would have already fired hours earlier. The light does not arrive all at once. A supernova has a shape in time, what astronomers call a light curve, and that shape carries information. In the first hours after the explosion, the brightness climbs steeply as the shockwave tears through the star's outer layers. The rise can last hours or days depending on how large the progenitor was. Then comes the peak, then the decline, and this is where the two main types of supernovae become easy to tell apart. A type 1. A supernova fades in a way that is almost clockwork. The peak brightness is followed by a decline that follows a specific rate, slowing after about 3 weeks, then fading more steadily for months. The reason for this regularity is radioactive decay. The explosion synthesizes large quantities of nickel-56, which decays into cobalt-56, which decays into iron-56. Each decay step releases energy that keeps the ejector glowing. Because the amount of nickel produced is tied to the Chandrasekhar limit mechanism, it is consistent from one type 1a to the next. The light curve is predictable enough that astronomers use it as a calibration tool. If you know how bright the explosion actually was, and you measure how bright it appears, you get the distance. That calculation has been used to measure distances across billions of light-years. Core collapse supernovae are less uniform. Some of them show a plateau in the light curve, a period where the brightness holds roughly steady for weeks before resuming its decline. This plateau comes from a shell of hydrogen-rich material around the star that recombines as it cools, releasing energy at a roughly constant rate. Other core collapse events decline more linearly. Some show multiple peaks. The variety reflects the variety of the stars that produce them, their mass, their composition, how much of their outer envelope remained at the moment of explosion. What both types share is this: the light curve is not just a record of how bright the thing was. It is a physical signature. The rise time encodes the size of the progenitor. The peak brightness reflects how much radioactive nickel was synthesized. The shape of the decline tells you about the density and composition of the ejected material. The brightness is spectacular, yes, but the spectacle is secondary. The way the light fades after the peak carries almost as much information as the peak itself. It is a record of the physics of the explosion written in light. Everything a star makes through normal fusion, from hydrogen all the way up to iron, goes somewhere when the star dies. The explosion tears the star open and scatters everything it ever built across hundreds of light years of space. Those scattered atoms eventually cool, drift, clump together, and become the raw material for the next generation of stars, planets, and in at least one case we know of, people. This is not a metaphor. It is a description of a physical process that has been running in this galaxy for roughly 12 billion years. To understand why supernovae matter for chemistry, you need to understand what a star can and cannot build on its own. A star spends most of its life doing one thing, fusing lighter nuclei into heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes neon, oxygen, silicon. Each step releases energy because the product is more tightly bound than what went into it. The star is essentially converting mass into energy at every step, and that energy is what holds the star up. The periodic table, in this sense, is a star's fuel log. Every element up to iron is a record of a fuel that was burned. But normal fusion inside a star, outside the violent conditions of a supernova, is actually limited in another way too. It only builds elements in a fairly direct path. To build elements between the main products of fusion, elements like selenium, barium, or lead, you need a different process. This is where neutrons come in. Deep inside aging giant stars, a process called slow neutron capture occurs. Physicists call it the S process. An atomic nucleus absorbs a free neutron. If the nucleus is unstable after that addition, it undergoes beta decay and converts the neutron into a proton, which bumps it one step up the periodic table. Then it absorbs another neutron. Then maybe another decay. The key word is slow. This process happens gradually, over thousands of years of stellar evolution, one neutron at a time. The S process is responsible for building roughly half of all the elements heavier than iron. Elements like strontium, barium, and lead are largely the products of this quiet, patient process happening inside stars that are in no rush. The S process has a ceiling though. It cannot build the heaviest elements. The nuclei get too unstable before neutron capture can push them further up the periodic table. To get past that ceiling, you need an environment that is absolutely saturated with neutrons and hot enough to drive reactions faster than any normal star can manage. You need a supernova. When the core of a massive star collapses and the shockwave tears outward through the star's layers, the temperatures in that shockwave reach into the billions of degrees. That number is worth sitting with for a second. The core of the Sun is about 15 million degrees. The shockwave of a core collapse supernova is several hundred times hotter than that. At those temperatures, nuclear reactions that would otherwise be completely impossible become not just possible, but rapid. Nuclei that would take thousands of years to build in a normal stellar environment get assembled in seconds. The flood of neutrons released during the collapse is extraordinary. Free neutrons are everywhere, and atomic nuclei absorb them faster than they can decay. This is the rapid neutron capture process, the R process, and it is responsible for roughly the other half of all elements heavier than iron. In a matter of seconds, the supernova is manufacturing nuclei that no star could ever produce through patient, slow process chemistry. The shockwave is a factory running at an insane speed, and it runs for only a few moments before the conditions disperse and the reactions stop. Then the explosion flings all of it outward. Every element made inside the star over millions of years of fusion, and every element forged in the few seconds of the explosion itself, gets scattered into the surrounding space. Here is why this matters to you specifically. The oxygen you are breathing right now was fused inside a massive star that died before our solar system existed. The carbon in every cell of your body came from helium fusion in a stellar core. The calcium in your bones was built in the oxygen-burning and neon-burning stages of a massive star's final years, then thrown into space when that star exploded. The iron in your blood, every atom of it, was synthesized in the silicon-burning stage of a star in its last days, accumulated in the core that then collapsed, and distributed through the galaxy in the explosion that followed. None of those atoms were created here. None of them were created in our sun. Our sun is a second or third generation star, meaning it formed from gas that had already been through at least one cycle of stellar birth and death. The cloud of gas and dust that collapsed to form our solar system about 4.6 billion years ago was already chemically rich. It carried the ashes of dead stars. Those ashes became the planets, the oceans, and eventually the organisms walking around on one of those planets, asking questions about where everything came from. The answer, in every literal sense, is supernovae. Not as a poetic description of cosmic connection, but as a factual account of where atoms have been. The oxygen, carbon, calcium, iron in a human body have specific histories of nuclear processing inside stars that lived and died long before the sun turned on. The atoms you are built from were processed through at least one supernova, probably more, before they ended up in the cloud of gas that eventually collapsed into our solar system. Iron is not the top of the periodic table. There are 118 confirmed elements, and fusion inside a star can only build you as far as number 26. Everything past that point, gold, platinum, uranium, iodine, barium, cesium, every single one of those elements needed something far more violent than a star quietly burning. They needed a different forge entirely. The process that builds them has a name. Astronomers and nuclear physicists call it the R process, which stands for rapid neutron capture. To understand why it works, you have to understand what stops fusion from getting past iron in the first place. Binding energy is the key. Fuse two lighter nuclei together and the product is more tightly bound. You release energy, and the reaction drives itself forward. Iron sits at the peak of that curve. Past iron, fusing nuclei together costs energy instead of releasing it. A normal stellar core cannot pay that price, so fusion stops, and anything heavier than iron has to be built through a completely different mechanism. Neutron capture is that mechanism. Instead of smashing nuclei together, you add neutrons to an existing nucleus one at a time. The nucleus absorbs the neutron, becomes unstable, and eventually decays into a new element with one more proton. Do this slowly, over thousands of years, in the deep interior of an aging star, and you get what physicists call the S process, slow neutron capture. The S process builds a range of elements, but it has a ceiling. It cannot get you to the heaviest ones. The decays happen fast enough to keep pace with the captures, so the nucleus never climbs very high up the table before it stabilizes. The R process is something else entirely. For it to work, you need a neutron flux so intense that nuclei are absorbing neutrons faster than they can decay. The nucleus climbs. It picks up neutron after neutron, becoming increasingly unstable, but the environment is so dense with free neutrons that it keeps absorbing them before it gets the chance to fall apart. In seconds, nuclei that started somewhere in the middle of the periodic table are climbing toward the heaviest elements in existence: gold, platinum, osmium, uranium, thorium. All of it assembled in a matter of seconds under conditions that essentially nowhere else in the universe can replicate. The question that drove decades of argument among physicists was simple. Where exactly does the R process happen? Core collapse supernovae were the leading candidate for a long time. The logic was straightforward. When a massive star's iron core collapses, the density in that core becomes so extreme that electrons are forced into protons, converting them to neutrons by the billions. The resulting neutron star releases a flood of free neutrons into the surrounding material. The temperatures are in the billions of degrees. The densities are nuclear. If the R process needs extreme neutron density and extreme temperature, a collapsing stellar core seems like an obvious match. For decades, models were built around this assumption. Textbooks included it. The problem was that the numbers didn't quite work. Simulations of core collapse supernovae kept running into difficulties, getting the conditions right in the right place at the right time. The neutron-rich outflow from the forming neutron star, the region called the neutrino-driven wind, seemed promising, but consistently fell short of what the R process required. The theoretical match was imperfect, and the evidence was indirect. Then, in August of 2017, a different source announced itself. Two neutron stars in a binary system, both the remnants of dead massive stars, had been spiraling toward each other for hundreds of millions of years. They finally collided. The merger produced gravitational waves detected simultaneously by both LIGO detectors in the United States and the Virgo detector in Europe. Astronomers swung telescopes toward the source within hours. What they found was something that had been predicted but never directly observed: a kilonova. The collision had produced a brief, intensely bright transient glowing across multiple wavelengths, and the spectra matched freshly synthesized heavy elements. Strontium was confirmed. The infrared glow was consistent with the production of large quantities of gold and platinum. In roughly 1.3 seconds of collision, that single event had forged heavy elements in quantities that dwarfed anything a supernova could plausibly account for. One neutron star merger, and the universe had made more gold than our sun contains in total mass. This changed the debate significantly. It did not end it. The current scientific picture is that neutron star mergers are almost certainly the dominant R process site for the heaviest elements: gold, platinum, uranium, while core collapse supernovae may still contribute meaningfully to lighter R process elements further down the table. The two sources are not mutually exclusive. The universe uses both, possibly at different proportions across different epochs of galactic history. Early galaxies may have relied more on supernovae simply because neutron star mergers take time. You need two massive stars to form, both to die and their remnants to slowly spiral together over millions or billions of years. The timing matters for understanding why different galaxies have different chemical signatures. What is not debated is the result. The iodine in your thyroid was built in one of these events. The uranium in any nuclear reactor came from a neutron star merger or something equally catastrophic. The gold in any ring, anywhere on Earth, was forged in conditions so extreme they still cannot be fully reproduced in any laboratory. The history of astronomy is partly a history of watching things that were not supposed to be there. For most of human civilization, the sky was considered fixed. The planets moved, the moon cycled, the sun rose and set. But the stars themselves were eternal. They were the backdrop, the unchanging frame around everything else. That idea held for thousands of years across dozens of cultures. Then, every few centuries, the sky would break its own rules. A point of light would appear where none had been before, blaze for weeks or months, and then quietly disappear. People called them guest stars. They did not know what they were. We do now. The oldest confirmed supernova in the historical record appeared in the year 1006. The constellation Lupus, low in the southern sky, suddenly had a new member. Astronomers in Egypt, Iraq, Switzerland, and China all recorded it independently. A physician in Cairo named Ali ibn Ridwan described it as roughly 2.5 times the diameter of Venus and bright enough to cast shadows. Chinese imperial astronomers noted it in their official records and tracked it for almost 2 years. Some accounts suggest it was visible during the day. Modern measurements of the remnant, which still exists roughly 7,200 light-years away, confirm this was not a comet or a planet. It was a star dying, and for a few months in the early 11th century, it was the brightest object in the night sky other than the moon. 48 years later, the sky broke the rules again. In July of 1054, Chinese astronomers reported a guest star appearing near the Horn of Taurus. Their records describe it as visible in daylight for 23 days. For nearly 2 years, it remained visible at night. Arab and Japanese accounts corroborate the timing. Some researchers believe petroglyphs in the American Southwest may also depict it, though that connection remains debated. What is not debated is what that explosion left behind. Today, at the precise coordinates the Chinese astronomers recorded, you can point a telescope and see the Crab Nebula, a tangled, still expanding cloud of gas and magnetic filaments spreading outward at roughly 1,500 kilometers per second. At the center of the Crab Nebula sits a pulsar, the spinning neutron star the explosion created, rotating 30 times per second. The 1054 event is one of the most studied supernovae in history, and its remnant continues to be one of the brightest sources in the X-ray sky. The Chinese astronomers who noted it in their court records had no way to know what they had witnessed. They were watching the birth of an object that astronomers still study 1,000 years later. Then came 1572. On the night of November 11th, a Danish astronomer named Tycho Brahe was walking outside when he noticed a brilliant star in Cassiopeia that had not been there the previous evening. He described his own reaction honestly. He could not believe his eyes. He asked servants nearby if they saw it too. They did. Tycho measured its position precisely over the following months and confirmed that it showed no parallax, no shift in apparent position relative to nearby stars as Earth moved in its orbit. That meant it was not a comet, not a planet, not something nearby. It was in the realm of the fixed stars. This was a direct challenge to the Aristotelian cosmology that had structured Western intellectual life for centuries. The idea that the heavens were perfect, eternal, and unchanging could not survive a star appearing and then vanishing. Tycho published his observations in a work called De Nova Stella about the new star, and the phrase stuck. We still call these events novae and supernovae, partly because of the language he chose. The remnant of his star, Tycho's supernova remnant, is still detectable today as an expanding shell of X-ray and radio emission roughly 8,000 light-years away. 32 years after Tycho, in October of 1604, another new star appeared, this time in Ophiuchus. Johannes Kepler tracked it for over a year. It reached a brightness comparable to Jupiter at its peak. Galileo lectured about it publicly. Kepler's detailed measurements contributed to the slow dismantling of the idea that celestial objects were fixed and immutable. Like Tycho's observation before it, the appearance of a new star where no star had been was philosophically inconvenient for the prevailing model of the cosmos. Kepler's supernova remnant sits about 20,000 light-years away. It is still expanding, still detectable across multiple wavelengths, and then nothing. The sky went quiet. More than 400 years have passed since Kepler watched that new star in Ophiuchus fade. In that entire stretch of time, no supernova in the Milky Way has been bright enough to see without a telescope. That is a long silence. The Milky Way is estimated to produce somewhere between 1 and 3 supernovae per century on average, based on observations of comparable galaxies and indirect evidence from our own. By that estimate, somewhere between 4 and 12 supernovae should have occurred in our galaxy since 1604. None of them were visible from Earth. There are two likely explanations. One is statistical bad luck. Even at 2 per century, the timing is random, and long dry spells are possible. The other is dust. The center of the galaxy is heavily obscured. A supernova on the far side of the galactic plane might be completely hidden from optical telescopes by intervening gas and dust. Astronomers have found evidence of recent supernova remnants in the radio and X-ray sky that have no recorded optical counterpart, which supports the dust explanation. Cassiopeia A, one of the brightest radio sources in the sky, is the remnant of a supernova that almost certainly occurred in the 17th century. Nobody wrote it down. By every statistical estimate, several supernovae should have occurred in the Milky Way since Kepler watched his in 1604, and none of them have been visible from Earth. On the night of February 23, 1987, a Canadian astronomer named Ian Shelton was developing a photographic plate at the Las Campanas Observatory in Chile when he noticed a bright new point of light in the Large Magellanic Cloud. He walked outside to confirm it with his own eyes. It was there, naked eye, unmistakable. He had just become the first person in nearly 4 centuries to watch a new supernova ignite in the local neighborhood of our galaxy. The news moved fast. Within hours, observatories across the southern hemisphere were pivoting instruments toward the same patch of sky. By morning, the astronomical world knew what it had. The star that exploded had a name before it died. It was catalogued as Sanduleak -69 degrees 202, a blue supergiant sitting roughly 168,000 light-years away in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way. This was already unusual. Theoretical models had predicted that the stars most likely to explode as core collapse supernovae were red supergiants, large, bloated, and cold. Sanduleak was a blue supergiant, hotter and more compact. That single detail immediately complicated the picture. Stellar physicists had to account for why a star that did not match the expected profile had exploded anyway. The answer, it turned out, involved the star's metallicity and evolutionary history, but the debate kept theorists occupied for years. What was not in doubt was what the star had done. It had collapsed, and it had done so in the most consequential way possible, within range of detectors that humanity had already placed underground. Here is where SN 1987A becomes something more than just a spectacular light show. On that same night, roughly 3 hours before Shelton noticed the brightening on his photographic plate, neutrino detectors on 2 separate continents registered something. The Kamiokande 2 detector in Japan picked up a burst of 12 neutrinos in 13 seconds. The IMB detector in Ohio recorded 8 more. The Mont Blanc detector in Europe caught a signal as well, though its timing has been disputed. In total, about 24 neutrinos from an event 168,000 light-years away had walked through underground tanks of purified water and left a detectable trace. 24 particles, out of roughly 10 to the 58th that were produced. That number deserves a pause. A core collapse supernova releases more energy in roughly 10 seconds than the Sun will radiate across its entire 10 billion year lifetime. Around 99% of that energy comes out not as light, not as the shockwave, not as the visible explosion, but as neutrinos. They flood outward from the collapsing core at nearly the speed of light, and because they interact so weakly with matter, they pass through the entire overlying star almost instantly. The shockwave, by contrast, has to physically fight its way through thousands of kilometers of dense stellar material. That takes hours. This is why the neutrinos arrived at Earth 3 hours before the optical brightening. The light we see from a supernova is not the collapse itself, it is the shockwave F, innerly breaking through the surface. The collapse already happened, announced only by a ghost signal that almost nothing can detect. Those 24 neutrinos confirmed something that generations of physicists had built careers on, but never directly verified. The core collapse mechanism, the idea that a dying massive star implodes and releases its gravitational energy almost entirely through a flood of neutrinos, was no longer just theory. It had a data point, a small one, an almost laughably small one against the scale of what produced it. But it was real, it was timed correctly, and it matched the predictions with enough precision to settle the central question. When physicists say SN 1987A was the most important supernova in scientific history, this is what they mean. The light was spectacular. The neutrinos were the proof. Astronomers have been watching the aftermath ever since. In the first years, the brightness of SN 1987A was partly sustained by the radioactive decay of nickel-56 into cobalt-56, and then cobalt-56 into iron-56, a predicted sequence that left a specific fingerprint in the light curve. The decay matched the theoretical predictions almost exactly. More confirmation. More check marks next to equations that had never been tested against a real event. What SN 1987? A looks like today is unlike anything else close enough to image in detail. The expanding shell of ejected gas has been illuminating a set of pre-existing rings, loops of material the progenitor star shed during an earlier phase of its life, tens of thousands of years before the explosion. As the blast wave catches up with these rings, it heats them, and they glow. The innermost ring has lit up in sections over the past few decades as the shock smashes into clumps of denser material, producing hotspots that have grown brighter and then faded in sequence. The Hubble Space Telescope has returned to this object hundreds of times, and every image is slightly different from the last. It is the only supernova remnant in history that astronomers have watched evolve in real time from the moment of explosion. The deeper question, what the core left behind, is still unresolved. The models predict a neutron star. The neutrino signal is consistent with a neutron star forming, but no pulsar has been confirmed at the center of SN 1987A, and for decades, the remnant was too optically thick to see inside clearly. Recent observations from the James Webb Space Telescope have found what appears to be a compact, hot source buried at the center, possibly the long-sought neutron star, finally becoming visible as the surrounding gas thins. Whether it is a neutron star or whether the core continued collapsing into a black hole is a question still being answered. The data is still coming in. SN 1987. A is still expanding, still glowing, still being watched by every major observatory. A laboratory of stellar death sitting at the edge of our galaxy, close enough to study in real time. A supernova does not end when the explosion fades. The light peaks, then drops, then dwindles to something telescopes can barely track. But the star is not done. What it leaves behind is a structure that will keep expanding, keep colliding, keep reshaping the surrounding galaxy for thousands of years after the original flash has gone cold. These remnants are among the most studied objects in astronomy. The more closely scientists examine them, the more work they turn out to be doing. The Crab Nebula is the most famous example. In July of 1054, Chinese astronomers recorded a guest star in Taurus, bright enough to see in full daylight, visible for 23 days under the sun and nearly 2 years in the night sky. What they were watching was a supernova roughly 6,500 light-years away. Today, that explosion has left behind a tangled, glowing web of gas and dust nearly 11 light-years across, still expanding outward at about 1,500 kilometers per second. At its center sits a pulsar, a neutron star spinning 30 times every second, blasting radiation into the surrounding cloud and keeping it energized nearly 1,000 years later. The Crab is not a remnant in the sense of something finished. It is an active system, driven by a dead star that refuses to stop radiating. Cassiopeia. A tells a similar story. The supernova that created it probably went off around 1680, though for reasons that are still debated, no clear naked-eye observation of it was ever recorded. What we have instead is the remnant, a roughly circular shell of superheated gas about 10 light-years in diameter, expanding at close to 6,000 kilometers per second. X-ray observatories have mapped its structure in extraordinary detail. The ejecta from the original explosion is visible in distinct chemical layers: silicon here, sulfur there, iron in specific regions. A preserved snapshot of the onion shell structure the star had just before it collapsed. Cassiopeia A is not just beautiful, it is a record of the star's interior, scattered across several light-years of space. The Veil Nebula is older and fainter, the remains of a supernova that exploded somewhere between 10,000 and 20,000 years ago in the constellation Cygnus. It stretches across roughly 110 light-years now. The shockwave has slowed considerably as it sweeps up surrounding material, but it is still moving, still compressing the gas it runs into, still heating the interstellar medium in its path. You are looking, when you look at the Veil Nebula, at a wave that was launched when our ancestors were still in the Stone Age and has not stopped traveling since. That shockwave is doing more than just expanding. As it pushes into surrounding gas clouds, it compresses them. Dense enough compression can trigger collapse. Collapse produces new stars. The supernova that ended one star's life may directly cause the formation of others. This is not a speculative idea. There is isotopic evidence embedded in the oldest minerals of our own solar system, specifically the presence of certain aluminum and iron isotopes that could only have been produced recently in a nearby supernova, suggesting that a stellar explosion may have triggered the collapse of the cloud that became the Sun, the planets, and everything on them. The supernova that seeded our solar system with heavy elements may also have been the event that started it forming in the first place. Then there is the matter of cosmic rays. For most of the 20th century, the origin of the high-energy particles constantly striking Earth's upper atmosphere was an open question. These particles arrive from all directions, carry enormous energies, and show no obvious source. The leading explanation now is supernova remnants. As a remnant's shockwave moves through the interstellar medium, charged particles can bounce back and forth across the shock front repeatedly, each pass accelerating them a little more. Over thousands of years, this process can boost particles to energies far beyond anything a human-built accelerator has ever achieved. The particles eventually escape and scatter throughout the galaxy, and some of them end up hitting Earth. The cosmic rays streaming through your body right now, at this moment, were almost certainly accelerated in the shockwave of a dead star. The chemical contribution alone would make supernova remnants worth studying. Everything the star synthesized over its lifetime, every atom of oxygen and silicon and calcium and iron fused across millions of years, gets mixed into the interstellar medium as the remnant expands. The next generation of stars that forms in this region will be born from gas already enriched with those elements. The planets that form around those stars will inherit them. This is how the galaxy's chemical complexity has grown over billions of years, not smoothly, but in pulses, each supernova injecting a new round of heavy elements into the surrounding space and raising the baseline for everything that forms afterward. A single remnant can stay active in this way for tens of thousands of years. The shockwave sweeps outward, slowing but never quite stopping until it has merged with the general turbulence of the interstellar medium and become indistinguishable from its surroundings. Even then, the elements it distributed remain, folded into whatever structure the galaxy builds next. The remnant is still working, still pushing, still seeding the medium around it with everything the star ever made. Because all Type 1a supernovae explode through the same mechanism, and at nearly the same mass. They all reach roughly the same peak brightness. That single fact turns a dead star into a measuring stick. Think about what that means. If you know exactly how bright something is, and you can measure how bright it appears from where you're standing, you can calculate the distance. It's the same logic you'd use with a streetlight. A streetlight looks dimmer the farther away it is. If every streetlight on Earth put out the exact same wattage, you could figure out how far away any one of them was just by how faint it looked. Type 1. A supernovae are streetlights. Incredibly bright, catastrophically violent, remarkably consistent streetlights, visible across billions of light-years of space. Astronomers call objects like this standard candles. The term goes back to the early days of measuring cosmic distances, when researchers needed some reliable reference point they could trust. Cepheid variable stars were the first useful ones, stars that pulse with a period directly tied to their luminosity. But Cepheids are not bright enough to see across truly enormous distances. Type 1. A supernovae are a single white dwarf detonating at the Chandrasekhar limit releases enough energy to be detected at distances that dwarf anything Cepheids could reach. By the 1990s, observational technology had advanced to the point where these distant explosions could actually be measured carefully enough to be useful. Two independent research teams decided to use them for something ambitious. The goal was to measure how the expansion of the universe was changing over time. Everyone understood that the universe was expanding. Edwin Hubble had established that in the 1920s. The question was whether that expansion was slowing down. Gravity pulls matter together. The combined gravitational attraction of all the matter in the universe should act as a brake on the outward expansion. The further back in time you look, the faster things should have been moving apart, because gravity has had less time to slow them down. That was the expectation. It was a reasonable expectation. It was also completely wrong. The two teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were looking at Type 1a supernovae in distant galaxies. Distant enough that their light had been traveling for billions of years before reaching our detectors. When light travels for that long, the expansion of the universe stretches it. The stretching is measurable. It's called redshift. By comparing the redshift of a supernova to its apparent brightness, you can reconstruct exactly where it was when it exploded and how fast that region of space was moving away from us at that moment in cosmic history. Both teams ran the numbers, expecting to find that ancient supernovae were closer than a naive calculation would suggest, because back then, the expansion should have been faster, and gravity should have been reeling it in since. That is not what they found. The distant supernovae were dimmer than predicted, not brighter, dimmer, and dimmer means farther away. They were farther away than they should have been if expansion had been decelerating. That meant the expansion wasn't slowing, it was speeding up. The universe was not coasting to a gentle halt. Something was pushing it outward, and that push was getting stronger over time, not weaker. Both teams double-checked their data, then checked again. The signal was real. In 1998, they went public with results that upended cosmology. Physicists reached back to a term Einstein had used and then abandoned, the cosmological constant, and attached it to something newly mysterious. Dark energy, a name for whatever is driving the acceleration, which is to say a name for something nobody actually understands. Dark energy doesn't interact with matter the way gravity does. It doesn't cluster. It fills space uniformly and appears to push outward on the fabric of the universe itself. Current estimates suggest it makes up roughly 68% of the total energy content of the universe. It is the dominant ingredient in the cosmos, and we have no clear idea what it is. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel Prize in Physics in 2011. The citation was straightforward. They had discovered that the expansion of the universe is accelerating. What the citation didn't fully capture was how strange the path to that discovery had been. It started with a dead star, a white dwarf that had spent millions of years quietly stealing mass from a companion, crossed a precise threshold, detonated in a runaway thermonuclear explosion that lasted seconds and left nothing behind. No neutron star, no black hole, just light, and that light carried enough information, encoded in its brightness and redshift, to reveal one of the most fundamental properties of the universe. The calibration is not perfect. Astronomers now know that Type 1a supernovae are not all exactly identical. There are small variations that need to be corrected for, and the correction methods have been refined significantly over the past 2 decades. But the basic principle holds. You see the light, you measure how bright it is, you compare it to what you expect, and the universe tells you something true about itself. Every supernova in the survey was a data point. Thousands of dead white dwarfs, scattered across billions of light-years of space, collectively revealed that the cosmos is not winding down towards some quiet equilibrium. The universe is not just expanding, it is expanding faster over time, and the evidence came from counting the light of dead stars across half the observable universe. There are stars in the Milky Way right now that are going to explode. Not metaphorically, not eventually in some abstract cosmic sense. Some of them are already in the final stages of the process described in the last several sections of this video. Iron cores building up, outer shells stacking like rings, the countdown running invisibly behind a surface that still looks calm from 650 light-years away. The galaxy produces roughly 1 or 2 supernovae per century. The last one visible from Earth was in 1604. The math is not comforting. The star most people point to first is Betelgeuse, that red giant in Orion's shoulder, the one that dimmed so dramatically in late 2019 and sent the internet into a spiral, is a genuine red supergiant and a genuine supernova progenitor. Everything about it fits the profile. It has roughly 15 to 20 times the mass of our Sun. It is puffed out to about 1,400 times the Sun's diameter. It has already burned through most of its available fuel. At some point, it will explode. When it does, it will be visible in daylight from Earth. The problem is the timeline. Betelgeuse is probably tens of thousands of years from its final collapse, possibly longer. The dimming event was almost certainly a surface mass ejection, followed by dust formation. Dramatic, but not a death notice. Betelgeuse is not the most likely candidate for the next visible supernova. It is just the most famous one. Eta Carinae is a different conversation. It sits about 7,500 light-years from Earth, deep in the southern sky in the constellation Carina, and it is extraordinary even by the standards of massive stars. Best estimates put its mass somewhere around 100 times that of our Sun. Some studies push that figure higher. A star that massive is burning through its fuel at a rate so extreme that it is consuming in thousands of years what our sun will take billions to exhaust. Eta Carinae has already demonstrated instability. In the 1840s, it underwent a massive eruption, not a supernova, but a giant outburst that briefly made it the second brightest star in the sky. It ejected several solar masses of material in a period of years, forming the homunculus nebula, a double-lobed shell of gas and dust still expanding around it today. That kind of behavior is what you expect from a star running out of options. Eta Carinae may already be in its final stages. It may be centuries from exploding. It may be decades. Nobody knows. Then there is WR104. This one concerns a smaller number of astronomers, but the concern is specific. WR104 is a Wolf-Rayet star, a category of massive star that has shed most of its outer hydrogen envelope through extreme stellar winds. They burn hot, they burn fast, and they die violently. What makes WR104 unusual is its orientation. The star appears to be pointed almost directly at Earth, and Wolf-Rayet stars are considered strong candidates for producing gamma-ray bursts when they collapse. A gamma-ray burst from a star aimed at us, even at roughly 8,000 light-years away, is a different kind of event than a standard supernova. The energy is not distributed in all directions. It is focused into a jet. The subsequent sections in this video will address the danger question directly. For now, WR104 is worth knowing about simply because it is the kind of candidate that makes astronomers pay close attention. Beyond these names, there are likely dozens of massive stars scattered through the galaxy in advanced evolutionary stages that have not been individually catalogued as candidates. The galaxy is large. Dust in the galactic plane blocks our view of most of it. Several supernovae may have already gone off in the Milky Way since 1604, hidden entirely behind the dense material between us and the galactic center. We would not have seen them. We would not have known. Some of those explosions might be generating expanding remnants right now that no telescope has found yet. What has changed in recent decades is that we now have the ability to catch the next one even before its light arrives. Neutrino detectors built for other purposes, Super Kamiokande in Japan, IceCube at the South Pole, the Sudbury Neutrino Observatory, are sensitive enough to detect the neutrino burst from a core collapse supernova anywhere in the Milky Way. The neutrinos escape the collapsing core hours before the shockwave reaches the star's surface. That means detectors on Earth could receive a signal and trigger alerts to every observatory on the planet before the explosion is even visible in the sky. The system exists. It is called SNEWS, the Supernova Early Warning System, a network of detectors linked together to cross-check signals and eliminate false positives. The first confirmation of a neutrino burst from multiple detectors will go out to astronomers within seconds. Automated sky surveys are also running continuously. Systems like the Zwicky Transient Facility and the Vera Rubin Observatory scan enormous areas of sky on short timescales, flagging anything that changes brightness unexpectedly. Gravitational wave detectors, built to catch merging black holes and neutron stars, would potentially register the asymmetric collapse of a nearby massive star. Every layer of the detection infrastructure built over the last 30 years is, among other things, waiting for the same event. The next Milky Way supernova will not sneak past us. When a massive star in this galaxy finally crosses the threshold, whether it is Eta Carinae or WR104 or a star nobody has named yet, the detection will be global and immediate. Whatever it is, when it goes, every instrument humanity has ever built will be pointing at it within minutes. The question people ask first, once they understand how much energy a supernova releases, is whether one could kill us. It's a fair question. The numbers you've been hearing throughout this video, the brightness of 1 billion suns, the energy output that dwarfs entire galaxies, the shock waves moving at a fraction of the speed of light, all of that naturally leads somewhere. And the honest answer is yes. Under the right circumstances, a supernova can absolutely threaten life on Earth. The more useful question is how close it would have to be. The danger does not come from the light. A nearby supernova would be spectacular, visible in daylight, casting shadows at night. But visible light, even at extreme intensities, is not what kills a biosphere. The real threat arrives in forms you cannot see. Gamma rays are the primary concern. A supernova releases an enormous pulse of gamma radiation in the first moments of the explosion, and at close enough range, that pulse would interact with Earth's upper atmosphere and start breaking apart the nitrogen and oxygen molecules that form ozone. The ozone layer is not just a chemical curiosity. It is the shield that blocks the sun's ultraviolet radiation from reaching the surface. Strip it away, and UV exposure at ground level rises dramatically. Photosynthesis collapses. The base of the food chain dissolves. Life does not end instantly, but the damage cascades through ecosystems over years and decades. High-energy cosmic rays are the second mechanism. A supernova remnant accelerates particles to extraordinary speeds, and those particles stream outward for thousands of years after the initial explosion. At close range, the increase in cosmic ray bombardment at Earth's surface would raise radiation exposure significantly. For complex organisms with long reproductive cycles, that kind of chronic radiation load is genuinely dangerous. It would not be an instant extinction. It would be a slow pressure on every living thing, compressing genetic diversity and pushing vulnerable species toward collapse. So where is the line? Researchers have run the numbers repeatedly, and the estimates converge on a threshold somewhere between 25 and 50 light years for a typical core collapse supernova. Get closer than that, and the ozone depletion becomes severe enough to threaten the biosphere in a meaningful way. Most estimates put the truly catastrophic zone inside about 25 light years, with meaningful but survivable damage extending out to perhaps 50. For the most energetic events, hypernova explosions, superluminous supernovae, or any event where a gamma-ray jet happens to be aimed directly at Earth, that danger zone expands. Some models push it out to 160 light-years or more for a direct jet. That is a much larger bubble of concern. Now look at Betelgeuse, 650 light-years away. That is more than 10 times the outer edge of the conservative danger zone. If Betelgeuse exploded tonight, every person alive would see it. It would be one of the most astonishing events in human history. It would not be dangerous. The gamma rays would still arrive, and instruments would detect them. But the intensity at this distance falls off with the square of the distance. By the time it gets here, it is a scientific event, not a survival event. The same applies to Eta Carinae at 7,500 light-years and every other known candidate discussed in the previous section. They are nowhere near the threshold. What makes this question unsettling is not the present sky, it is the past. The geological record contains several events that researchers have struggled to fully explain with terrestrial causes, and some of them have attracted serious attention from astronomers. A 2019 study found elevated concentrations of iron-60, a radioactive isotope produced in supernova explosions, in ocean sediment layers dating to around 2.5 million years ago, and again at roughly 8 million years. Iron-60 does not form naturally on Earth in significant quantities. Finding it embedded in ancient seafloor rock is a direct fingerprint of supernova material that reached this planet. The timing of the stronger deposit aligns loosely with a transition in Earth's climate and some disruption in marine ecosystems at the end of the Pliocene. Was a nearby supernova responsible for driving early human ancestors out of forests and onto open savanna by cooling the climate? That specific claim has been made in at least one peer-reviewed paper, and it remains controversial. The evidence is suggestive rather than definitive, but the iron-60 is real. Something exploded near enough to salt our ocean floors with supernova debris, and it happened while our ancestors were alive. That is not a theoretical exercise. The Ordovician extinction, roughly 450 million years ago, killed about 85% of marine species. It remains one of the least understood of the major extinction events. Some researchers have proposed that a gamma-ray burst or nearby supernova could have triggered the initial ozone depletion that drove that extinction. The hypothesis is not the consensus view, but it has not been ruled out either. The geological signal is difficult to read at that distance in time. The honest summary is this: the universe has been occasionally dangerous to life on Earth, and there is real evidence that stellar violence has touched this planet before. But occasionally is the key word. In 4.5 billion years of Earth's history, no supernova has come close enough to end everything. Life has survived whatever arrived. The events that left traces in the rock were disruptive, possibly catastrophic for some species, but not terminal. And right now, looking at every star within the relevant distance, none of them are candidates. The current sky does not contain any known candidate star within the danger zone, which is probably why we are still here to ask the question. Step back from the physics and the timescales and the classification schemes, and what you are left with is something simpler. The universe does not just destroy things, it builds with the wreckage. Every supernova that has ever gone off scattered material into the surrounding gas, and that material was more chemically complex than anything that existed before the star formed. Hydrogen and helium were the starting inventory. Everything else had to be earned, one stellar generation at a time. The first stars had almost nothing to work with. They formed from hydrogen and helium, burned hot and fast, and died in explosions that seeded the galaxy with the first traces of carbon and oxygen and silicon. The next generation of stars inherited those traces. They fused them further. They built iron cores. They exploded in turn. Each cycle left behind a slightly richer medium, a slightly more complex chemistry, a slightly better foundation for whatever came next. That process has been running for roughly 13 billion years, and you are near the end of it. The calcium in your bones was forged in the core of a star that died before our sun existed. The iron in your blood came from a supernova. The oxygen you are breathing right now was produced in a massive star's shell burning phase and scattered by an explosion millions of years before Earth formed. These are not metaphors. These are the actual histories of actual atoms currently inside your body. They were somewhere else before this. They will be somewhere else after. You are a temporary arrangement of elements with a very long backstory. What makes this strange is the scale of the violence involved. We are not talking about gentle processes. A core collapse supernova releases more energy in a few seconds than our sun will release across its entire 10 billion year lifetime. The shockwave that distributes those elements travels at thousands of miles per second. The temperatures that forge the heaviest atoms are measured in billions of degrees. And at the end of all of that, the result is iodine, calcium, gold, the quiet chemistry of living things. The most destructive events the universe produces are also, in a very literal sense, the source of the most intricate structures it contains. Every generation of stars has been more chemically equipped than the one before it. Ours is a late generation. The sun formed from a cloud that had already been enriched by many previous cycles of stellar birth and death. The planets formed from the same cloud. Life emerged from the chemistry that the planets inherited. This is not a coincidence or a lucky accident layered on top of blind physics. It is just what happens when you run stellar evolution long enough and let the explosions do their work. The galaxy right now contains stars at every stage of this process. Some are just forming, collapsing out of gas clouds that are themselves the remnants of older explosions. Some are in the middle of their hydrogen-burning lives, stable for millions or billions of years. Some are near the end, fusing heavier and heavier elements, building iron cores in the dark. Some of them have already collapsed in the time it took to make this video, and the light from those explosions is crossing space right now, years or centuries away from reaching any eye or instrument that could detect it. You cannot watch any of this happen in real time. The timescales are too long, or the distances too great, or both. But the night sky is a record of where the process stands right now, at this moment in the galaxy's history. Every point of light up there is a fusion reactor in some stage of its countdown. Most are nowhere near the end. Some are closer than we think. The signals, when they come, will arrive without announcement. A star that has been a fixed point in the sky for your entire life will simply get brighter one night and keep getting brighter. The night sky is full of countdowns, and most of them are running without any warning system at all.